Greeting, ladies and gentlemen. My name is Sophanyka Sith, and in this video here, I will be explaining how to use PermaLearn, which is a 2D structural analysis tool. Before I guide you through all the tool that has in PermaLearn, let me introduce you to this book, which is The Fundamental of Structural Analysis with Addition. And I will be using this book to solve some exercise so that it will be easier to understand how to use the tool in PermaLearn. So the website is called PermaLearn, and you can either search it on Google, PermaLearn, or find a website that show you this type of picture. So let me go through it. Okay, so as you can see here, it's a 2D structural analysis tool, and it has all of this tab that you can put all of your input, and it also show your output here at the solution. So here, as you can see my mouse pointing it, this is the grid that. So this is the grid that will show your member when you input some other number, and it will also show your solution here as well. And on the right side here, we have force component calculator. I will explain to you soon. So number of finite element here, this means that the higher the number it has here, the more smoother the internal force and the formation diagram it has that it shows. And the grid size here, as you can see, 10 meter by 10 meter. So the grid size will show up in this place right here. So if you want it to be bigger, you can select it and it go up to 100 meter. Okay. And here is the mesh size. So the mesh size, as you can see here, it is 1, and you can have it until 0.1 meter, and also you can have the bigger number too, like for example 100. And the unit system here, it has SI and BG. So SI here is the international standard system, and BG is the British system. And once you change it, don't forget to put the save option. And then as you can see here, the grid size go up to 100. Mesh size is also 100 as well. It doesn't show here, but when you input the number, it will show it. And yeah, it's in BG unit system as well. As you can see, it is now in fit. So these are all the system. These are all the setting. And on the top right corner here, you can see the help button. So the help button here, you can take a look for a while if you want, because it will show how to use each of tool as well. And then there's also a demo video that you can go on YouTube, and something you want to learn about this website, and you can also switch it to light mode if you prefer. But since I prefer dark mode, I will go with dark mode. All right. So to understand all of this option right here, let's solve some exercise so that we can walk through it. So by looking at that book, we have this exercise here, P0.1. So they want to determine the reaction of a structure in figures P3.1. So let's take a look at this structure first. What is its dimension? What does it have? What are the load and what are the support? So you need to understand the structure first before you hop on the website. So as you can see here at A, we have a pin, we have a load that also making it an angle, and linear distributed load. And here is a roller. And the length of this structure is 13 feet. Okay, now after we take a look at it and understand it quite well, let's go to the website. So first we need to start with the setting. So look at my mouse right here on the right. Since it has 13 feet, I will go with 20 feet. So you can go higher than 20 to 100, but it will be harder since it's gonna be so small on the display. And you cannot put 10 as well since it's less than 13. So the website gonna say you cannot put it that way. So 20 is the best fit. And the mesh size, I think number 1, let's put 1, is the best. And the unit system is also BG. And after you put all of it, don't forget to put save option. Okay, now you're done with the setting. So for this exercise, for the cross section, it's not really necessary. So I can go straight to the member. Okay, so here it said begin X coordinate, begin Y coordinate, horizontal distance from the begin point, and vertical distance from the begin point. So I want to start my member at exact X, at the and the x coordinate equal to 0 and y equal to 0, so I can just leave it like that. And since the member is 13 feet and it's go horizontally to the right from this axis, so I can just type 13 and then add it. Okay, so now we have joint A and joint B, and when you put your mouse on this joint, it will show you what the website call your joint. So at here, at x 0 by 0, it is called joint A, and the second joint, which is joint B, is at x equal to 13 feet. Okay, now after we have our member, let's go to support. So for the support, I hope you remember, here at A, it is a pin, and B is a roller. So as you can see here, it said joint coordinate. So we pick A, which is a pin. And here we have many options such as fixed pin and roller. Since it's a pin, I will add pin. And another joint, which is joint B. So go to joint coordinate and click B, and the support type is roller. So as you can see here, it also trying to ask us what is the inclined angle of the roller. So if our roller have an inclined angle, you can input it, but since this one doesn't really make any angle, so it is 0. But for example, let's say it is a vertical roller, then you can input 90 degree. Sorry. So 90 degree here and then add, right? And then if we show that it is a vertical roller here. However, since our exercise says that it is just a horizontal normal roller, then I can just go to this edit tab. So it is this vertical roller is at ID number 2, and it shows its x coordinate at 13 feet. So we can just go here, erase this, and then click edit. Okay, now we're done with the support. Let's go to hinge. So the hinge, we don't really have hinge for this exercise, so we can skip it. And for joint load, so joint load here are the load that apply on the joint. So from this exercise, we don't really see any load that actually apply on the joint, only this distributed load here. But we don't use this tab yet. So for the load that is not on the joint, we can use this tab, which is called point load. Okay, so first they ask for the member ID. Since there's only one member, you just member number 1. And for the load orientation here, I will explain in another exercise. Distance from the beacon joint. So I want to input this 10 kips, So 10 kips load. So it's distance from the beacon joint, which is A, is 4 feet. So we put number 4. All right. What is the horizontal force? What is the vertical force? And what is the couple moment? So this load, it make vertical load and also horizontal load. However, we don't know what is the magnitude of it. Okay, so we want to find what angle does it make. Okay, so from geometry, I know that the angle it made here is 53, okay, 0.13 degree. Please don't mind my writing. Okay, and the angle here, it should be 36.87. So force component lateral, the force magnitude, as I remember, is 10. Okay. And it's rotational angle. So as you can see here, it said that counterclockwise. It's positive when it is counterclockwise. And since the rotational angle of the force magnitude is 36.87, so we just put it, and then we put calculate. Okay, now we have the result of it. But please be mindful of this result that gave you. Be mindful of the sign. The magnitude, we can copy it right through here, but the sign is not. So it said that the horizontal load, it go to the right, and the vertical load, it go down. But reality, okay. So in our exercise, the horizontal load, it go to the left, and the vertical load, it go down. So we need to be mindful of that because this calculator, it's just they're just importing cosine and sine. So the vertical load is 6. So we put here as 6, and since it is going to the left, we put minus, and the vertical force is -8. It's minus because it's going down and there's no moment. So close this and then add it. And then we have it. And then another tab is called linearly distributed load. Okay. So since we have only one member, we choose this member. And again, we skip this one. And it's load type. So our exercise here is a vertical load. It's going down as 5 kip per fit for fit. And the distance from the beginning of the distributed load is 9 feet away. So remember this. Now go back. Vertical load distance from the begin joint. So the begin joint here, and this is this start here. So the distance from the beginning joint is 9 feet. Let me just put 9 feet. And the distance from the end joint is 0. Here, it added the end of the structure. Okay, 0, we can skip it. And the begin load, it starts with -5 and it also end with -5. Please be mindful with this unit here. It's keep perfect. This one is also keep perfect, so we don't really need to convert it. However, it is different from keeps perfect. You need to convert it in order to align with this system. Now we just put add, and then we have it. So we have all the support, the load, and everything else are all in set. The temperature change, we don't have it. Propagation error, we don't support settlement, we also don't. So we go straight to solution. Okay. So as you can see here, there are many display options. Have member, support, load, external effect, reaction force, normal force, shear force, bending moment, reverse, and deformation. So I'm going to show you guys what it can display. So if you can check and uncheck all of this to see what we really want to see. So I want to see only the member. So I click it and just show it. And then member with support, display it. Member, support, and load here. And external effect, since we don't have the external effect on this, so it don't show anything. And now here, I will output the result that we really want, which is the reaction force. So by just clicking this and put display, we can see the reaction force, which are the arrow in red. Okay. So here, by putting our mouse over the arrow, we can see that it's a reaction force, or x equal to 6 kips at joint A, and it also shows its coordinate as well. We go to another arrow. So the reaction force is all y equal to 8.6154 kips, and its coordinate. So be mindful that all y here, it means that the reaction force at the y-axis. Same here as well. All x is the reaction force at x-axis. And at joint B, its reaction force, it only had the vertical reaction force. So all y equal to 19.3846 kips. All right, after knowing its reaction force, if you're curious about normal force, you can display it as well. So just like the reaction force, you can put your mouse over it and then you can see its value. So the normal force at this point is -6. The same here and here and here as well. And then on this distance, it is 0. Okay, so now if you're curious on how, like, for example, if I want to know normal force at x equal to 0.5 feet, how do I find it? Since it's only show at x equal to 1 and x equal to 0. So that is when mesh size come handy. So if you want to find it at 0.5, you put 0.5. Okay, 0.5. It is also -6 kip. All right. Okay, then shear force. Okay, so the shear force so this one we show the shear force diagram, and the same as normal force, you can put your mouse over here to see all the value at different distance. The bending moment, display it. Bending moment, reverse. Okay, so if you only want to see the diagram, like you don't want this arrows like here, like if you think it's kind of messy, you can just uncheck all of this below here. If you want to find it with member, it's also fine. Only bending moment reverse is also fine as well. And then for the deformation. Okay, so this is the deformation of the structure. And we can't really know the value of it because we didn't put cross section. But in the next exercises, you will see the value because I will input the cross section there. Okay, so as I have promised you guys, I said that I will explain the load orientation, that's with respect to local coordinate system and with respect to global coordinate system. So in order to understand it, I need to modify this exercise a little bit. So first, I want to get rid of this load. So when I want to get rid of it, you can go to point load, which is where I input this load. And as you can see at the bottom here, in the word remove, just remove it. And then it's gone, just like that. So what I want to do is add another member. Okay, so I want to add it 4 feet from joint A. So its begin X coordinate should be 4, begin Y coordinate, the same should be 0. And I want it to be an inclined member with that it make an angle. So let's just say the horizontal distance is 3 and the vertical distance is 4. Okay. So here we get it. We have an inclined member. Now the biggest question. So we go to point load. So for point load here, now we have 2 member. The first member, we click here, it shows that it is in orange. So this one are the member number 1. And then we click number 2, it shows that this one is member number 2. Now for the global coordinate, it means that the X and Y axis is the usual way. So look at my mouse here. This one are the Y axis, and this, the horizontal, is the X axis. That is the global coordinate. Let me show you an example. So let's say the load on this member here, it is 2 feet away, for example, and it has a vertical force going down for 6 feet within the global coordinate. All right, then we add it. So as you can see, since it's the vertical force with respect to the global coordinate, so it will go down on the Y axis. However, if we put local coordinate system, it will be different. So instead of inputting all the number again, I can just go to the edit mode. Okay, and at load orientation here, I put with respect to local coordinate system and edit it. So now as you can see here, the load is going down vertically with respect to the local coordinate, and the local coordinate is the member here. And if you notice this dashed line down, below this member right here, it will show us the local coordinate of each member. So for member number 1 here, the dash line is below here. So it means that the its coordinate is the same as the global coordinate. However, with this member number 2, the dash line is this way. So it means that here it is the x-axis and here is the y-axis. All right. So I hope you guys understand that. For the linear distributed load, it's quite similar for that. Yep. So for example, on member number 2, and then I go to local coordinate, vertical load, let's just say 0 and 0, and then put 5, and the end load is also -5. So let's just say 0. Okay, here you see it is respected to the local coordinate. It will look like this. Now let's move on to another exercise. So P3.8 here is that determine the reaction at all support and the force transmitted through the hinge at B. Okay, so let's analyze the structure first. At A we have pin, B we have a hinge here, and C is a roller, and D is also a roller. And we have a load, vertical load here, and also a moment at this point. Now let's start. So before we start, let's clear all of this, proceed, and be mindful of the unit system. Let's side, let's go with 1. And this one, I believe it is 30 meter. Save option. I forgot to save. Okay. Now we have the setting. Let's do the member. So again, I will begin it at all at x0 and y0. Horizontal distance. So instead of the last exercise, I begin going 13 all the way. I want to try 5, 5, 5 over here instead. So okay. So when I want to start another point, I can either put this begin x coordinate at 5 manually, or just go to joint coordinate and find the joint that should start with. It will show it immediately. So the distance from begin point from joint B here, it's 5. Add it. And then again another 5. And another 5 as well. And at the end, I think it is 10 meters. Okay. All right. Now we have the member. Let's add the support. So at joint coordinate A, it is a pin. And then we have a roller at C, which is 15 meter. So see here, 15 meter. But on this, based on our input, it is at joint D. So we find joint D roller. And the N is also a roller that we add it. Okay. So we have a hinge at B. Then we go to the hinge tab. And it's 10 meter away. So based on this, it is joint C. Yes. And this one here, we show the member ID that the hinge connect what member, and it's connect member 2 and 3. So we add it for joint load. So as you can remember from the previous exercise, I go to point load because we don't have the load that apply on the joint. But since I input the member this way, it's mean that the load 40 kilonewton here, it will apply on this joint B. So we can just go to joint load and pick joint B. And vertical force is minus 40 because it's going down, and then add it. And then another joint load at 20 meter. At this point here, it's 16 kilonewton meter clockwise. So let's find it. 20 meter away, so it should be joint B. And this one, it said that it is counterclockwise positive. And since our is clockwise, then we put negative 16 and then we add it. And again, be mindful of this unit. If it's different from this, please convert it. Now I believe we have all of the pin, the rope. I mean, we have all the support and all the load. We can go to solution and find its reaction force. Okay. So again, you can put your mouse on it to find all the value. Moment here, mg, 5. Normal force, 0. Shear force. This is the shear diagram. Bending moment. All right. This one is reversed, so obviously it is different, just reverse version of this. And the formation, again, we have no value, but you can see how it deflected. All right, this is the end of this exercise. Let's go to another exercise. So exercise P11.26 here, it has point moment operated in the frame in figure P1126 by temperature change of plus 80 Fahrenheit in girder ABC. The coefficient of temperature expansion is alpha T equal to 6.6 times 10 to the power minus 6 inch per Fahrenheit. And E is equal to 29,000 kips per inch squared. Let's take a look at the structure here. So it has different eye. And at A is a pin, D is a pin as well, and at C is a roller. And it is in BG unit. So here 15 feet, 15 feet, and 20 feet. Okay, so unlike the previous exercise, this one we need to put the cross section. So, okay. So I fall to go to the setting first. This one, the grid size should be 40, and the unit system will be BG. Save option. And then it showed that they want us to input the cross-sectional area, modulus of elasticity, and moment of inertia. So our exercise, it tells us E, which is 29,000. So let's put it 29,000, and moment of inertia. So here it's at 200 inches to the power 200. Yes. And if we take a look at this exercise, they don't really tell us the cross-sectional area. So since for this type of exercise, the cross-sectional area don't really affect it much. So we can just input whatever number we want. So let's say in my case, I put 1 inch square, for example, and then we add it. And we also have another cross-section as well with the moment of inertia equal to 600 ABC here. And again, this one also put 1 and add it. Okay, now we're done with the cross-section part. Let's go to the member. Okay, to start this, we know that we can either start at D or A. So I want to start at D. If it start at D, then the begin X coordinate should be 15 feet away, right? So I put 15 here, and at D it's going up, not ordering, so it's not going to the right like the previous exercise. It's going up for 15 feet. So just 15 feet, and it is plus. And here it asks for cross-section ID. So its cross-section ID is number 1, because for number 1, it is, here you can see here, ID 1, its I is equal to 200. Okay. 15. This one's also 15. 1. Yes. And then add it. And another coordinate. So at A here, it is begin at the Y coordinate of 15 feet. So I just put 15. And it's going to the right for 15 feet. And its cross-section ID is 2. Let's see, join C here. When you click it, you can see the orange part. So it's also going to the right when we add it. Now we have the member. Let's add the support. Support A down here. It's pin. Let's just put pin. And then B, it also pin. So add it. And then C, there's no support. And D, it is a road. Now we have our support. There's no hinge. Let's put the joint load. Is there any joint load? No. Joint load also no. Distributed load also no. Temperature change, we have it. So I believe there is some error in display for this website. It say that it is Celsius and this one is also Celsius, but it is actually Fahrenheit. Okay, so please be mindful of this mistake. So the exercise tells us that it has a temperature change of plus 80 Fahrenheit in girder ABC. So which means the member A and member C here, it has a temperature change of 800 Fahrenheit. So let's see how AB here is at member ID 2. And it said positive when the temperature increases. So obviously our exercise say plus, so then it will increase. So 80 Fahrenheit. 80 Fahrenheit, and the coefficient of thermal expansion by 10 to the power of minus 6 is 6.6. So 6.6, and then add it. Let me show that arrow that will tell us what is going on here. It said that there's temperature change, delta T equal to 80 Celsius. Show the alpha, and it is on member number 2. Now we go to another member, which have the same in change in temperature and also in alpha, which is coefficient of thermal expansion. All right. Now I believe these are all of it. We go to the solution. So the only 2 exercise we don't see the external effects. Now we can see it, which are the temperature change. This arrow here. Okay, so the exercise they want to find the moment created in the frame in girder ABC. So what are the moment? So by this website, we can find it by going to the bending moment diagram of display, and then we can see it. All right. So these are the girder A, B, C. This A, B, and C. If you want to see its moment, we can click the arrow in it. But if you feel like it is really messy because it overlaps with another member, you can just unclick it. So for example, I want to see only member number 2, just display it. You see it. And then we can see the moment created at each point. And if you want a closer number like 11.5, you can just adjust the message size. Number 3 here. You can see this all as well. And after we have the cross-section ID, we can find its deformation and its value as well. Okay, so here is its deformation. And by clicking on it, we can see its value. So let me explain it by going through it one by one. So it says displacement dx equal to 0.06 inch. So it means that it's placed by the x-axis of 0.06. So it means that it's going to the right by 0.06, and dy, there's no change in the y-axis, meaning that it doesn't change vertically. And dz here, it shows the angle that it made. So at that point, the member, it rotates for minus 0.03 degree. And this one is at x equal to 15 feet and y equal to 8 feet for member number 1. And for other member, there's a bit displacement at the x or horizontally here. All right, let's go to another exercise. P 9.10. A. Solve problem 9.1 for the loading shown if support C settles 0.25 inch when the load is applied. Use moment at support A as redundant. Given E equal to 30,000 kips per inch square and I equal to 320 inch to the power 4. And I want to compare the result if I equal to 640 inch to the power 4. So they want to solve the problem at P 9.1. If the support C here is settled 0.25 inch when there's a loading here. Okay. So first let's analyze this exercise. We have the supported A fixed and C as a roller. Before we start another exercise, let's clear this off and take a look at our setting. This one I have 15 feet, so let's go with 20 feet. And BG, yes, and save option. Now let's go to cross section. Again, I will put this as 1. The modulus is 30,000. And it has 2i, so 320 for the first one. And the second one is 30,000, yes. Second one is 640 added. After we have the cross section, let's do this. So the horizontal distance for the begin point is 9 feet. Oh, so please don't forget to select the cross section. And then another is 6 feet. Okay. If you want to put 15 at the begin at this joint as well, it is also fine, but since I want to just the joint lock, so I will do it this way. Okay. So for the support at A, it is fixed. D is a roller. All right. And for joint load, B, the load is going down for 36 feet. Okay, minus 36. And add it. Okay, and then the exercise also say that the support C settles 0.25 inch for the loading show. I'll go to the support settlement at C. So it has a vertical settlement, obviously, and it is going down for 0.25. So we put minus because the sign here said that it's going up. It is positive when it is going up. And we add it, and we have it. So we put all of the input that we have, then we can find our reaction force. So here we have all y, reaction force, y-axis, moment, and also reaction force here. And also find the normal force, which is 0. Yes, shear force, bending moment, reverse, just reverse, and deformation. So since we have input our cross section, you can see the value. Displaced at x-axis is 0 inch. Displaced for y-axis is minus 0.25, like our support settlement, and it made an angle of 0.13 degree. So the exercise want to find the maximum deflection. They want to find a point that has it. So for the maximum deflection, its angle needs to be 0, right? So all we need to do is try and find where is it. So since I want it to be like smaller, I put 0.2, which is the minimum mass size to find the accurate one. All right. So let's see where is the angle is 0. Like where is it 0? So I believe it's around here. Let's go check. Here. It is very close to here. So it is at x equal to 10.4 feet. So at x equal to 10.4 feet, which is 10.4 feet away from the begin joint, it has the maximum displacement. And you can put your mouse over to see the order as well. Yeah. Okay, so the exercise also want us to find it at another cross section. So we can go to member and edit it. Edit the cross section ID. And then we see the solution. So the reaction force become like, I don't know, it's different. And shear force, bending moment, and then you can compare the result on the previous eye. So as well, you can also find the one that have maximum deflection. So yeah, yeah, it is around here, yes. So the maximum deflection is around here instead. 14.2. All right, it's done. Let's go to another exercise, P10.25. It said that if a member AB in figure P10.25 is fabricated 3/4 inch too long, determine the moment and reaction rated in the frame when it is erected. Sketch the deflected shape given E equal to 29,000 kips per inch square. So let's take a look at this. The horizontal is 24, and this one 12 feet. It also has different eyes as well. And at Z it is fixed, at A it is pin. Let's clear all of this. Okay. Let's look at the setting. The grid size should be 30, I suppose. And same option. Cross-section area again 0. Modulus elasticity set 29,000. And moment of inertia, the first one 120. Add. And then another one as well, which is 240. Then add it. All right. Remember, in coordinate 0 again, and it's going up for 12 feet. Okay, we need to select cross-section ID. So cross-section ID number 1, it is 200. And for this one, it's going to the right for 24 feet, and its cross-section ID is 2. Okay. If we go to support, FA here, it is a pin. And let's see, down here, it is fixed support. Okay, so now we have the support and all. Let's go to fabrication area. So it said that it is fabricated 3/4 inch too long. And member, what member is it? Member AB, so AB is here. So for here, it is member number 1. And this one here, it said that positive when a member is fabricated longer than design length. And here it said too long, so obviously it is longer. That is positive. 3/4 is 0.75 added. Great. Now we can find the moment reaction created in the frame. Go to bending moment. Yes. So by the fabrication error, the moment curve will look like this. But the formation, it is like this. If you want to see it better, let's adjust this for this member. Right. Okay. So around here, it's all 0. Oh, wait. Slight angle. And here. All right, so I have covered all of the tab from cross-section, member, support, hinge, joint load, point load, linearly distributed load, temperature change, fabrication errors, force settlement, and all of the solution tab. So if you have any more questions, you can go through the help tab by reading all of this to have a better understanding. So this is the end of the guide to PermaLearn on how to use it. Thank you so much for listening.